there are tables. Of course, the calculations can be done by you. You can do them by changing variables, but it's a lot of work. But in particular, the gradient in spherical coordinates I'm interested in right now. Okay, so if you look at the gradient function in spherical coordinates, meaning that f is going to depend on r, theta, and phi, right? Those are spherical coordinates. So if you look at the book, and then you look at the cover, you know, the back of the cover of the book, you will see something like this. That in spherical coordinates, this looks like df dr r hat. I'm using the standard notation that r hat means a unit vector in the radial direction. Okay, so and etc. plus 1 over r derivative of f with respect to theta in the direction theta plus 1 over r sine theta derivative of f with respect to phi in the phi direction. Have you ever seen this before? No. Okay. So luckily, at least for now, later on we'll need to come to more of that. But for now, I really don't need the whole thing. So what does this mean? Okay. So if you have a Cartesian system, x, y, and z, then, okay, we know exactly how the gradient works. It's the derivative with respect to x, the derivative with respect to y, the derivative with respect to z. How anybody can get this expression at all? Any idea? How you can do it? How would you do it?
Start with conversion first.
What's that?
Start with the conversion.
A table? Oh, a change.
Like, yeah, just like x equals r cosine theta.
Okay, perfect. Thank you. Exactly. Okay. So z is equal to r cosine theta, x equals r sine theta cosine phi, etc. Okay? And so then you have to make a change of variables. So everybody knows how to make, everybody's familiar with Jacobians. You heard Jacobians at one, no, if you didn't, that's, but at least I'm trying to figure out how much we can talk and how much we cannot. But it's not really that critical. The point is that there is a
Equilibrium is r squared sine phi.
Yes, yeah. So there is it's a matrix of derivatives. That is a transformation. But basically, we have a transformation from the variables Cartesians to the variable spherical. And so every time that we take a derivative with respect to r, theta, and phi, we can basically make a change of variables. So it's a generalization of what you do in Calculus 1 when you do change of variables, you know, between, for example, x equals y squared in an integral. You know, all of you know how to do that. dy 2 dy is equal to dx, etc. Well, that thing. So this is a generalization in more dimensions of that idea. Okay, so that's a way you can actually do that yourself. Okay, but what does it mean? It means that if you are trying to represent a point in spherical coordinates and the point is given by a distance r, okay, by an angle theta with respect to z, and this of course everybody's familiar with, and then if I make a projection of the point on the xy plane, it's going to intersect at some location, and that vector there on the xy plane will make, by definition, an angle phi with the x-axis. Okay, so if I am at that point and I want to play the gradient game, meaning how things change as I move in different directions. Remember when we introduced the gradient, one of the first things we did was to define the directional derivative. Yes, so how things change as we move in one direction or another, etc. So for example, one simple derivative that we could consider is to take that point and move radially. Okay? And so if we do that experiment and we look at the variations of the function f in the radial direction, then it turns out that that can be very simply obtained as the derivative of f with respect to r in the radial direction. That's sort of not surprising, it's very intuitive, right? So, okay? But the thing is, so the vector r here that I define is this thing, as you can expect. So r is the unit vector in the direction of r. This theta hat is the following. Okay, so for that one, you consider motions of the point that are on a circle. Okay, so for an easy way to picture that is you are on the Earth, okay, and you have meridians and you have parallels, correct? So now you are at a point. If you move on a meridian, you change your latitude, but not the longitude though. The longitude stays the same. So if you do that motion, then what you are doing is that you are changing your angle theta for a fixed phi. Yeah, phi actually tells you where you are, what longitude you are, but theta tells you your latitude. So by changing theta, you change your latitude a little bit, but your longitude stays the same. So when you do that, in that particular meridian, you define a unit vector that goes tangent to that big circle, and that's this unit vector theta. Okay? Make sense? Okay? So if I look at the picture I just described from the side, this would be the North Pole, and that corresponds to some meridian. Let's suppose that the longitude is equal to 0. So in that case, the meridian goes to what important feature on the Earth? Yes, if the longitude is 0, where does it go? No, of course, but that's extremely important longitude meridian, because it's yeah, and it goes through where? Yes, of course, it goes through, yes, North Pole and South, yes, I agree. No, but there is something, I'm pretty sure that you know that.
Like on the Earth?
Yeah.
Oh, it's red, no?
Ah, thank you very much.
It's just random.
It's no, it's not random. I mean, England was the power of the time.
I mean, it's not,
I understand. I'm joking. Yes, of course. It doesn't have anything to do with the Earth. Yes, but okay. So it's very close to London. Okay, because at the time they decide to be the reference. Huh?
it's the prime meridian. It's the Why did they choose London?
Why they chose Greenwich and not London?
Yeah.
Well, it's like a little suburb, but because that's where they had the observatory. So they got to decide.
Everything is in the middle of the map, right?
Of course, because they were basically ruling everything at the time. So they say, okay, this is 0.
We're in the middle.
Yeah, we're in the middle. But okay, so let's suppose that we take. So now that we understand what we're talking about, let's say that we take that meridian that goes to Greenwich, somewhere in here, and I join a line with that observatory, and I move a little bit to measure the changes of my function along that direction. So by definition, theta grows down. Okay, by definition. So the unit vector theta is this guy here. That's what it is. Okay? So the unit vector r is radial, the unit vector theta is that thing there. Now the unit vector phi, as you can imagine, is something very similar. Only that phi now varies on a circle in reality. Okay? So now if I stand on a parallel on the Earth, yes? So then phi hat is perpendicular to the axis of the Earth, to the line that goes between the North and South Pole. Okay, that's the phi, unit phi. Okay, so
that picture you drew is coming out of the board, into the board?
Which one? This one?
No, the
this one?
Yes.
No, this one is just planar. This is true.
If you imagine that in 3D, then D is coming out of
Oh, good. Thank you. That's a good idea. So in this picture, if I want to do the phi hat, it would be into the board. Yeah. a unit vector into the board. Okay, yeah, that's great. Yeah. Okay, so now we have a picture of what's going on. Okay, we will return to this gradient later, or at least to the spherical coordinates. But for now, we really don't need all this information. It's good to have it, but we need only partial information here. Okay, so really, I'm interested in this function 1 over r minus r prime cube. Yes? This function is a function of the magnitude of r minus r prime. It happens to be 1 over r minus r prime cube, could have been 1 over r minus r prime to the 7th power, or it could have been the exponential of the absolute magnitude of r minus r prime. Doesn't really matter. It's a function of the lamp object magnitude of r minus r prime, correct? Okay, so the meaning of r prime is that it's a fixed point in space, correct? So, since it's a fixed point in space, what varies is r, just for one moment, I can imagine that that's my origin. No problem, right? I can shift all my axes and say r prime, this is where I look from, correct? Okay, and in that case, just for one moment, I will undo that immediately. This depends on the magnitude of r minus r prime, but if I take r prime equal to 0, it depends on the magnitude of r cube. Okay, it depends on the magnitude of r alone. And so, if I take spherical coordinates, what is the magnitude of the vector r? What do we call it?
Radius. No,
okay, fine. Yeah.
Radius. Radius. Magnitude.
Yeah. See, it's okay. The concept is fine, what you just told me.
It's a normal vector to the...
But this is the magnitude.
That's going to be
So-
it's going to be the distance.
It is the distance, exactly. Okay, so if I think for a moment in spherical coordinates and I step at r prime, then this function that I have depends on the magnitude of r alone. It doesn't depend on the angle theta and phi.
And r is still from our old point system?
Okay, so the way we did this problem, if I just remind you again very quickly, so we have the origin somewhere. We placed our dipole here. It's very tiny, I don't care about it anymore. And then we observe from here. That's our geometry. So what I'm saying, since r prime is a fixed thing, as far as all the derivatives that we are taking, for a moment I can come and step here and look at things here. So from this perspective, of course, this vector is the vector r minus r prime. But what I notice is that that function here, not this one, but this one depends only on the magnitude of r minus r prime, and from this perspective, this is nothing but the magnitude of r, the distance.
You basically don't care about the theta and the phi.
Yeah, okay, this is going to be a huge simplification. It's going to be a huge simplification because the gradient, okay, in general, involves derivatives with respect to theta and phi, of course. Like if we do it in Cartesian coordinates, we have x, y, and z components. But in spherical coordinates, if we are dealing with a function that depends only on the magnitude of r, then this is the only term that matters. Is that clear? Somebody wants to contribute? Yeah.
But doesn't, if r was from our new observation point, then yes, but it's not.
It is. Well, no. I'm going to fix that in a second. You'll see. Yeah, but the point is, yes. But you see, I see what bothers you, and let me just make a quick comment. Because, of course, that if I insist on taking this point, things are going to be very messy. Because now there are phi and theta components there that I have to worry about. But I don't want to do that. I first want to get the concept that if I step here, then what I'm saying is true. And once we understand that, we are going to fix it immediately to take care of any angular dependence. But first I want to look from here, okay? So in that case, the gradient reduces simply to the derivative of f with respect to r in the direction r. Okay, very good. So now I'm going to fix it because we really are not necessarily looking for r prime. So what I'm going to do is write this in this weird way. Okay, so clearly, symbolically, like we've done before, I can get rid of the function f and just consider the operator and say that the gradient is nothing but the derivative with respect to r in the r direction. I mean, assuming that, that we can act it on a function if we want to. Okay, once we understand that, the meaning of r is simply the distance between the source and the observation point. I don't care if I call it r or I call it r minus r prime, because the physical meaning is that difference, okay? I'm just talking and I'm explaining intuitively what's going on. Of course, that if you are going to, you can do it longhand and you can prove exactly that it works. But, okay, so what I'm going to do now is to change this expression to a form that is useful for us. I'm going to consider this form of the gradient. Instead of the unit vector r, I can always, in general, write, let me do it on the side, right? Of course, that's true always, and even more, a little bit of notation. Okay, so it seems why are you writing so much, but you will see in a second. Okay, so if I know that that's true, now I'm going to write it in this form. Okay, the unit vector r, I'm going to write it as r vector over the magnitude, but now I'm going to include the r prime in case. And then this is the unit vector now in the direction of interest to me, which is this one. I'm observing from here, this is the vector r minus r prime, and this is the unit vector in that direction. Okay? R prime, remember, is a fixed vector. And then what should I write here?
The r minus r prime.
The derivative, yeah, with respect to what? Exactly, yeah. So perfect. Okay, so it's going to look like, in this case, it's a total derivative. It just happens with respect to r minus r prime. Okay.